we are now going to look at the Hessian matrix in parts. Derivative with respect to y, because I seek the mixed derivative where the slope is 0. That is, so let's see what happens if we introduce non-zero mixed derivatives. Now let's look at a little generalization of what we did previously. That is, now I have taken the same simple 2 by 2 Hessian matrix, but we have introduced a term for the function, that is xy, which actually makes the level curve of the convex bowl elliptical, that is an ellipse rather than a circle, which was the previous case. Now the global minimum remains there, so therefore the plane remains to be xy. That is, therefore, your equation of the plane is z equal to 0. It is equivalent to saying the tangent is parallel to x-axis in a single variable situation, where you are talking about a maxima or a minima. In both the cases, just like the tangent plane, the tangent line will be parallel to x-axis. Here the tangent plane continues to be parallel or coincident with the xy plane. Now, this Hessian matrix is constructed using the second order derivatives. These are pure second order derivatives, and these are mixed derivatives. In this case, why do we get the mixed derivative? That is because if you consider the function z equal to x square plus y square, we have introduced a term which is mixed, that is, has both x and y. So therefore, if I seek the first derivative with respect to x of z, then you can see that this turns out to be first partial derivative would be 2x, and of course minus, if you differentiate this with respect to x, you will get y, and therefore if I seek the second derivative of this, that is differentiating partially with respect to y, would land me at this value for the mixed derivative. Since it's a continuous function in x and y, so both the mixed derivatives have to have this particular value, and it's quite commonsensical to see. But first, if you differentiate, you'll get 2y minus x, so therefore that has to be minus 1. So therefore, earlier the same function we considered, but this term was missing. But this time we have deliberately added this term, and you can see the new convex ball whose level curve is an ellipse, and the Hessian matrix would now become, because of the mixed derivatives which were 0 in the earlier case, it would be 2, 2, minus 1, minus 1. So if you differentiate this for the second time, the second order partial derivative of z with respect to x remains 2. That means these values, that is the value of principal elements, are going to remain the same, but however, I caution you that the principal curvatures do not. Why? Because you have this diagonal populated. Whenever you have this full matrix, you cannot say these are principal curvatures. Then we'll have to evaluate what are going to be called the eigenvalues of the matrix. And let me remind you, even in your engineering, in many situations, be it electromagnetics, be it mechanical engineering, be it electrical engineering, everywhere, whenever you have a physical tensor, of course, most of the physical tensors have to be symmetric physical tensors. And when you seek eigenvalues, they represent the principal quantities, be it the inertia tensor, be it any other tensor, or be it the Hessian matrix which we are considering. The eigenvalues, remember, always represent the principal values. In a while, we are going to look at what are eigenvalues, how to evaluate it. But however, we advise you to visit our lecture on eigenvalues and eigenvectors and the graphical interpretation of the same, so that you would be able to follow our next lectures in great detail. But here I am just making a mention of eigenvalues, eigenvectors, because each eigenvalue, each principal value or principal curvature in our case has to be commonsensically associated with a direction, right? And that direction is going to be called the eigenvector, the value and the direction. Okay, so that when combined, we will make a meaningful interpretation, because you have to have principal curvature as the eigenvalue of this matrix, and there should be a corresponding direction of that curvature, which is going to be called the eigenvector. Before we discuss these concepts in detail, please go to our lecture on eigenvalues and eigenvectors, and then come back to the next lecture. But here I would like to make one important observation. As I said, what is the role of these mixed derivatives? They actually contribute to two important consequences. One is they do alter the value of principal curvatures. What were the value of principal curvatures? They were equal, and both was equal to 2. But now here you have mixed derivatives, so you would see that the eigenvalues are going to be called in to compute the principal curvatures, but they are going to be 3, 1 in a while. You are going to discover why exactly I am talking about this. So the introduction of mixed derivatives has one direct consequence, that it alters the value of principal curvatures. Number one. Number two, you can see that I told you that I have taken the reverse of the convex bowl to indicate my curvature directions, because the global minimum occurs at the origin. So that is the point where I have to seek my curvatures. And you see that I have marked out 2 tangents. Of course, this one is the maximum principal curvature, and this is the minimum principal curvature. And it's a matter of visual observation. You can see that this is a much flatter curve compared to this particular curve. So therefore, obviously, anybody with basic knowledge of geometry would say that this is a curve with a very small curvature, and this is a curve with very large curvature. But the radius of curvature will be the other way around, because radius of curvature is 1 by curvature, remember. So therefore, this has a small radius, this has a large radius. That way also you would like to interpret it. But very importantly, the second important consequence of introducing the mixed derivatives is that the direction of the curvatures, which are given by the tangents drawn at the point where you are actually seeking the curvature, you can see that it no more coincides with the independent axis direction, independent variable axis direction. See, you can see that the minimum curvature does not coincide with x, the maximum curvature does not coincide with y. So therefore, they actually have rotated. Okay, the curvature directions actually have rotated, and as a consequence, the directions also have to be computed using this Hessian matrix. And one of the tools to do so is the evaluation of eigenvectors, which we are going to discuss next. So it is very important that the role of the mixed derivatives are understood. It actually majorly contributes to 2 things. One is it alters the value of the principal curvatures, and though principal curvatures continue to remain orthogonal to each other, see, that property is not changed. Now, how do you determine the new directions that are of the principal curvatures once you introduce the mixed derivatives, and what are the values, numerical values of the new principal curvatures that are got because you introduced the mixed derivative by altering the convex bowl by adding a xy function. Rather, you subtracted minus xy. Of course, the orientation will change. Now it has rotated in the anti-clockwise sense, it could rotate in the clockwise sense. So that is the only difference. If you were to consider plus xy, you could interpret that. You can play around if you have a graphical calculator at disposal, but this is what is to be observed very carefully. So the numerical value of the principal curvatures and directions both have been altered thanks to the mixed derivatives. Now let's move on and then discuss the Hessian matrix from the perspective of eigenvalues and eigenvectors. And also one more very important thing I would like to mention incidentally, that the product of principal curvatures is also called the Gaussian curvature, which is a very important measure, be it the pattern recognition, the shape recognition, or be it the deep learning. So very important. So once you compute the principal curvature, you can also compute the Gaussian curvature. In the forthcoming discussions, we would also give a graphical interpretation of the Gaussian curvature measure. So let's move on and look at more discussions. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.